Good evening. Look up on any clear night and you can see thousands of stars, all of different colours and sizes. Our Sun is a star, a perfectly ordinary star. It is so brilliant because we are in orbit around it at a safe distance, which makes it so easy to study. I encourage you to discuss the Sun's activity with members of your local astronomical society, where more experienced observers will be on hand to show you how to observe the Sun safely. I must stress one point because it is so important. Do not look at the Sun through any telescope or binoculars. Focusing all of the Sun's light and heat onto your eyes will cause permanent blindness. Accidents have happened in the past, so please be careful. Global Sun Day will take place on the 5th of July 2015, when astronomical societies worldwide are encouraged to participate and show the Sun safely to their members and the general public. The event has been coordinated by Pamela Shivak, who has a Facebook page dedicated to the occasion. On Earth, the Sun is important to all of us. Without it, life would be impossible and there would be no changing seasons. The winter season begins on the 21st of December as the Earth moves in the near side of its orbit. The Earth's axis is tilted by 23.5 degrees to the plane of its orbit around the Sun. In June, the North Pole is tilted towards the Sun and it is midsummer in the Northern Hemisphere. The North Pole has daylight all the time and the South Pole has no sunshine at all. By December, the conditions are reversed, with winter in the north and summer in the south. Only at the equinoxes, around the 21st of March and September the 22nd each year, are the hours of daylight and darkness equal all over the Earth. The seasons have little to do with the Earth's changing distance from the Sun, and we are actually at our closest to the Sun in northern winter. The distance then is only 147 million kilometres, as against 152 million kilometres in July. Winter in the southern hemisphere is longer and colder than winter in the north, while the summer is shorter and hotter. The Sun is a star. There is nothing remarkable about it. By stellar standards, it is neither very large nor small, and in luminosity it is very average. Astronomers class it as a dwarf star, though it is only fair to add that dwarf stars are much more common than giants. The only reason the Sun seems so much larger and hotter than the other stars is that it is so much closer to us. Our galaxy, the Milky Way, contains upwards of 100 billion stars arranged in a spiral formation. It is so huge that if you could travel at the speed of light, it would take you 100,000 years to travel across the main disk. Our Sun lies 26,000 light years away from the galactic centre. The whole Milky Way is revolving around, carrying the Sun with it. It takes our Sun 228 million years to complete its journey. Astronomers call this the cosmic year. Of course, the Sun is a great deal larger than the Earth, and its vast globe could contain more than 1 million bodies the size of our world. For anyone who would like some more facts and figures, the Sun's volume is 1,303,000 times that of the Earth, its mass 333,000 times that of the Earth, and its diameter is 1,392,000 kilometres. Its specific gravity is 1.4. In other words, the Sun weighs 1.4 times as much as an equal volume of water would do. Remember that the Sun's density increases greatly towards the centre of the globe, while its outer layers are comparatively rarefied. Like all normal stars, the Sun is made up of gas. The bright surface, known to astronomers as the photosphere, is at a temperature of over 5,500 degrees centigrade, while near the core the temperature rises to the incredible value of about 15 million degrees. Pass sunlight through a glass prism and it comes out as a rainbow of colour called a spectrum. Two dark lines in the yellow part of the sun's spectrum correspond exactly to the two bright yellow lines produced by the element sodium, and so we can prove that there is sodium in the sun. All of the 92 naturally occurring elements have been identified there. One, the gas we call helium, was found in the sun before being tracked down on the Earth. It is the lightest of all gases, apart from hydrogen, and is very plentiful in the universe. Hydrogen is being turned into helium in the process called nuclear fusion, and this is why the sun radiates. Analysis of the sun by means of the spectroscope shows that the most common substance there is hydrogen, which has been found to be the main fuel which keeps the sun shining. The atom of hydrogen is the simplest of all, since it consists of a nucleus which is made up of a single proton around which moves one planetary electron. Deep inside the sun, where the pressures and temperatures are so high, strange things are happening. The hydrogen nuclei are combining to form nuclei of the next lightest gas, helium. It takes 4 hydrogen nuclei to make up one nucleus of helium, and in the process a little mass is lost and a little energy is released. It is this energy which keeps the sun shining. The mass loss amounts to 4 million tons a second, so that the sun now weighs considerably less than it did when you first started watching this program. But the sun is so massive it will not alter noticeably for 5,000 million years. The photosphere is made up of high pressure gas so that it gives a rainbow or continuous colour. Surrounding the photosphere is a layer of much thinner gas called the chromosphere, which would be expected to give an emission spectrum. But in fact, the gases in the chromosphere are capable of absorbing those wavelengths which they would normally emit. Therefore, the lines appear dark instead of bright and show up as the dark Fraunhofer or absorption lines crossing the background rainbow. It is a complex area which astronomers are now studying in detail using the NASA spacecraft Interface Region Imaging Spectrograph, or IRIS, which was launched on the 27th of June 2013.
The secrets of the sun are hidden in how energy travels up through its layers out into space. The sun's energy starts in its core, a giant fusion engine where hydrogen atoms are turned into helium atoms. The energy produced there moves up through the convection zone to the sun's surface, the photosphere. Moving magnetic fields contribute extra energy along the way. As energy moves outward, the temperature continually drops. This is just as one would expect while moving away from a heat source.
Up until that point, everything makes sense in that the hottest part is in the middle and everything gets gradually cooler as we move away. But then something very interesting starts to happen, which is that it starts to get hotter again.
This layer, where the temperature mysteriously begins to rise again, is called the chromosphere. It lies in an interface region between the photosphere and the corona, the hottest and outermost region of the sun's atmosphere. The interface region is the greatest source of ultraviolet light that impacts the Earth and the space around it. Only a specifically designed spacecraft can image the wavelengths of light needed to study the chromosphere. Advanced computer modeling will enable scientists to interpret the data and better understand how the energy moves through the chromosphere.
The light from the chromosphere is difficult to interpret because of the complicated interaction that the light has with the matter. It bounces around, if you will, many times before its final bounce towards us. And this means that that interaction between light and matter needs to be modeled.
It takes only a small fraction of the chromosphere's energy to power the corona.
Although the corona is extremely hot, millions of degrees, it's at a low density, so it doesn't actually take a lot of energy to heat it to that temperature. The chromosphere, on the other hand, is a much higher density, albeit lower temperature. And there's much more energy deposited in the chromosphere than the corona. So that a tiny fraction of that energy in the chromosphere escaping into the corona is plenty to power all of the processes that we see, from heating to such extreme temperatures to driving the solar wind that fills the whole solar system, impacting all the planets, including our own.
Data collected from IRIS has shown that the interface region of the Sun is significantly more complex than previously known. This includes features described as solar heat bombs, high-speed plasma jets, tiny flares and mini tornadoes. These features are an important step in understanding the transfer of heat to the corona. The corona is a magnificent pearly white halo that you can see around the Sun during a total solar eclipse. The temperature of the Sun's corona is over 1,000,000 degrees centigrade, yet it is not actually as hot as it seems.
I've got, first of all, a child's sparkler. I'm going to put on a glove for this one. A child's sparkler, and if I put that into my gas flame and I light it, we are going to get showers of sparks. At least I hope we are. There we are. Now, I'm perfectly happy to put my hand near that and let the white-hot sparks fall on it, because although each spark is white-hot, it contains so little mass that it's quite harmless. Now, also here, I have got a red-hot poker, or at least it should be red-hot. No, it isn't even that, but it's been in a gas flame for some time, and it is very hot. And I assure you, I'm just not going to grip that with my hand. I'd be very sorry if I did. But the temperature of this poker is much less than the temperature of each individual spark. But watch, when I plunge the poker into a bucket of water, tremendous hiss. Because although the temperature was lower, the actual amount of heat was very much greater than with the sparkler. And it's the same, you see, with the corona. The temperature's high, but there's not very much heat.
There is observable detail on the Sun's surface. I must stress one point because it's so important. Do not look at the Sun through any telescope or binoculars. Focusing all the Sun's light and heat onto your eyes will cause permanent blindness. So please be careful. The safe method is to use your telescope to project an image of the Sun onto a piece of white card held behind the eyepiece. This video shows the Sun at the beginning of 2014. The most interesting features are the sunspots, which are darker patches against the brilliant photosphere. The temperature of a spot is about 4,000 degrees centigrade, well below that of the surrounding surface. A spot appears dark only by contrast. If you could see it shining on its own, its surface brilliance will be greater than that of an arc lamp. A large spot is made up of a darker central part, or umbra, surrounded by a lighter area, or penumbra. The shapes are often very complex. Sunspots tend to appear in groups. A group generally takes the form of two main spots, a leader and a follower, with various smaller spots around. What astronomers term solar maximum occurred recently, which is when the largest number of dark sunspots is on view, and some of these have been very big. This is a sunspot that came into view 6 weeks ago. It covered an area the size of a giant planet Jupiter, and it was visible to the unaided eye through thin cloud at sunset. This large sunspot was visible in February 2014 and went right around the Sun almost 3 times. Since the Sun's surface is made up of gas, we cannot expect the spots to be permanent, and we find that their lifetimes are limited. A major group may persist for weeks or even months, but small ones may vanish in only a few hours. The shapes and forms change constantly, and the life story of a group is fascinating to follow. A sunspot cannot be seen constantly all through its lifetime. The Sun spins on its axis in a period of about 25 days, so that as it turns, the spots are carried from one side of the disk to the other. Eventually, the spot will vanish over the edge or limb to reappear in 2 weeks on the opposite limb, if it still exists. Some large groups survive long enough to cross the disk 3 times. It is notable that when a spot nears a limb, it is foreshortened, so that a spot which is really circular will seem to be drawn out into an ellipse. The Sun shows a roughly regular cycle of activity. Every 11 years or so, it is exceptionally energetic, and there may be many spot groups visible at the same time. Activity then dies down, and at solar minimum, the disk may be free of spots for weeks at a time. But then the activity builds up once more until the next maximum is reached. The cycle is not completely regular, but it is very marked. We are now at sunspot maximum, and during 2014 there have been a small number of huge sunspots in view. There were maximum in 1990 and 2000, with minima in 1996 and 2008. In 1990 the Sun was extremely active. The current maximum is much weaker than the previous two. The next minimum can be expected around the year 2020. The sunspot cycle is by no means perfectly regular. The mean value of its length since the year 1715 has been 11.4 years, but there are marked fluctuations. The longest interval between successive maxima has been 17.1 years between 1788 to 1805, and the shortest has been 7.3 years between 1829 to 1837. Since 1715, when reasonably accurate records began, the most energetic maximum was that of 1957. There are spells when the cycle seems to be suspended, and there are few or no sunspots. One of these periods is known as the Maunder minimum. In 1894, the British astronomer Edward Walter Maunder found from examining old records that between 1645 and 1715 there were virtually no spots at all. This coincided with a very cold spell in Europe during the 1680s. In London the River Thames froze every winter, and frost fairs were held on it. Aurora too were lacking. Edmund Halley recorded that he saw his first aurora only in 1716 after 40 years of watching. Sunspots are often associated with temporary patches known as faculae, Latin for torches, which lie at high level. Faculae often appear in areas where a spot group is about to break out and persist for some time after a group has vanished. Under good conditions, it can be seen that the Sun is not uniformly smooth. Granular structure is evident, and this shows that the whole surface is in a state of constant turmoil. At this point, I should say something about how best to make observations of the Sun, although today most amateur astronomers prefer to photograph the Sun's visible surface to record the fine detail each day. The safest method is to project the Sun's disk onto a piece of white card held behind the eyepiece, and for this the card needs to be held in a light box or attached to a rod fixed to the telescope. The Sun's projected image should be at least 150 centimetres, about 6 inches, and a circle of this size is lightly drawn onto the card with an east-west line across the diameter. This is because the orientation of the Sun changes month by month, and the east-west diameter of the Sun needs to be carefully lined up with those on the card. The actual daily drawing of a telescope is made in a matter of minutes, and often advantage can be taken of quite small breaks in the cloud. It is also almost a matter of honour for a keen solar observer to obtain his daily drawings whenever the Sun appears, even to the extent of sacrificing a breakfast. Coming indoors and at any convenient time, the blank with the sunspot's positions marked is completed by filling in the remaining details. Of course, it is much better to have an astronomical notebook for your daily observations rather than separate sheets of paper. For each disk drawing, you must record the date, which should be given with the year first, followed by the month and then the day. The time, universal time, should always be used, followed by the telescope size and magnification. Then the seeing conditions. The kinds of remarks to enter are clear boiling haze, thin fog, thin cloud, drifting clouds, wind vibration, but by far the most frequent condition met with on any clear sunny day is boiling, which means that our atmosphere is very disturbed, causing ripples over the sun's image and a wavy limb. Spots go in and out of focus as you watch, and the smaller spots become invisible. There is a really nice computer program by Les Cowley called The Tilting Sun 3. Here is a link for you to download it. The software will give you all of the additional information that you need to include in your astronomical notebook. The rotation number, or CR, the Sun's mean rotation period is taken as 25.38 days and is numbered in sequence. At the beginning of 2014, the rotation number was 2145, and at the end of this year it will be 2158. P is the position angle of the north end of the axis of rotation, with plus if east and minus if west. BO is the latitude of the centre of the Sun's disk, plus or minus indicating the tilt of the axis towards or away from us. LO is the longitude of the centre of the disk or of the central meridian. If you are making regular observations of the Sun, I recommend that you join the Facebook group Solar Activity, all one word, which presently has over 11,600 members. Again, the administrator is Pamela Scheibach. One special occasion that everyone looks forward to each year is an eclipse of the Sun. The Moon moves around the Earth moves around the Sun. Therefore, there are times when the three bodies line up, with the Moon in the mid position. The result is what is termed a solar eclipse. Eclipses are of three types: total, partial and annular. At a total eclipse, the photosphere is completely hidden and the sight is magnificent. As soon as the last segments of the bright disk is covered, the Sun's atmosphere flashes into view and the chromosphere and corona shine out together with any prominences which happen to be present. The sky darkens sufficiently for planets and bright stars to be seen, the temperature falls sharply and the effect is dramatic by any standards. To either side of the main cone of shadow, the eclipse is partial, and the glorious phenomena of totality can never be seen. Many eclipses are only partial and not total anywhere. Finally, there are annular eclipses, from the Latin annulus, meaning a ring. When the alignment is perfect, but the Moon is near its greatest distance from the Earth, its disk is then not large enough to cover the photosphere completely, and a ring of sunlight is left showing around the dark mass of the Moon. For obvious reasons, a solar eclipse can only happen when the Moon lies on the Sun side of the Earth and is therefore new. If the lunar orbit lay in the same plane as that of the Earth, there will be an eclipse every month. But in fact the Moon's orbit is tilted at an angle of just over 5 degrees, so in general the new Moon passes unseen either above or below the Sun in the sky. From any particular point on the Earth's surface, solar eclipses are less common than lunar eclipses. This is because to see a solar eclipse, the observer has to be in just the right place at just the right time, whereas a lunar eclipse is visible from any location where the Moon is above the horizon. The next total solar eclipse will be that of the 20th of March 2015, and it will be visible from the Faroe Islands, while much of northern Europe will then see a large partial eclipse. Instead of waiting for a total solar eclipse to occur, it is possible to cut out all of the light except for that of hydrogen with special filters and study the chromosphere directly. We can then see flame-like projections of gas around the edge of the sun's disk, prominences, and long, dark, straggly features, filaments. Prominences and filaments are suspended in the sun's atmosphere by magnetic forces and are often to be found along the boundary between regions of opposite magnetic polarity. The weight of the gas in the prominence, which can be 100 times denser than the surrounding corona, is supported by magnetic field lines. When such a cloud lies between us and the photosphere below, it appears dark because it is absorbing the light from the photosphere. When it projects beyond the limb, it is bright because we can then see the light emitted by the hot hydrogen against the blackness of space. Eruptive prominences can surge outwards at speeds of hundreds of kilometers per second. Low-density prominences can hang almost unchanged for many days. All are of vast size compared to the Earth. A flare is a sudden and dramatic release of pent-up energy stored in the twisted magnetic fields associated with complex spot groups and magnetically active regions. A flare releases radiation at all wavelengths, from gamma rays to radio waves, but mainly as X-rays. Subatomic particles such as protons and electrons are accelerated to nearly half the velocity of light, and masses of high-temperature plasma, a mixture of protons and electrons, are sent hurtling outwards, sending shock waves through the corona and across the face of the sun. Flares are triggered by a process known as magnetic reconnection. Magnetic field lines behave rather like elastic strings. When they are stretched and twisted, they contain a great deal of energy which can be suddenly released. If an elastic band is stretched and then suddenly released, it snaps back and is quite capable of propelling a paper pellet across the room. In a similar way, if oppositely directed magnetic field lines are pushed together by the movement of hot plasma in the chromosphere or corona, the lines can come into contact, releasing vast amounts of energy as they do so. Plasma at the point of reconnection is heated to tens of millions of degrees, hot enough to give off X-rays. Charged particles are accelerated along the field lines and blobs of plasma are catapulted out through the corona. Magnetic reconnection drives all aspects of solar activity. They determine the shape and structure of the corona and play a major role in perhaps the most dramatic of all events, coronal mass ejections, or CMEs, in which vast shells of plasma with intertwined magnetic fields are catapulted out through the corona into space. Each CME contains around 1,000 million tons of plasma. They hurtle outwards at speeds ranging from 200 to 2,400 kilometers per second. The underlying field lines control the way in which the plasma flows, while the shapes of CMEs can be very complex. Plasma is escaping from the corona all the time in what is called solar wind, where closed loops of magnetic fields in the corona are strong enough they trap the million-degree plasma and prevent it from escaping. However, in other parts of the corona, the field lines do not form closed loops, that is to say, they are open and hot plasma can readily escape. These leaky areas of the corona are known as coronal holes. A major outburst, such as a flare or CME, sends out a burst of energetic particles into space. When these particles reach the Earth, they squeeze and distort the magnetosphere, causing electrical currents to flow. This produces magnetic storms, which deflect compass needles, cause power surges in electric cables, and cause charged particles to plunge down magnetic field lines in the area of the Earth's north and south magnetic poles. The particles interact with atoms and molecules in the upper atmosphere, making them emit light and producing displays of the aurora. Aurora are often referred to as the northern or southern lights. They tend to occur in oval bands centred on the magnetic poles and are best seen from high latitudes, though after a major solar eruption the auroral bands expand to produce displays visible much closer to the equator. The Sun will not be around forever. Though the core contains vast reserves of hydrogen fuel, enough to maintain it for another 5,000 million years, the supply will eventually run out. When the core has used up its available fuel, it will shrink. As it does so, its temperature will rise and hydrogen will start to burn in the shell surrounding the original core. In consequence, the Sun will actually become brighter and will swell up to become a huge distorted red giant, 40 to 50 times larger than it is at the moment. The temperature of the Earth's surface will soar, the oceans will boil, surface rocks will melt, and the atmosphere will be driven off into space, so that life here will no longer be possible. A few 100 million years later, the Sun's nuclear furnace will switch off, the outer layers will be puffed out into space, and what is left of the Sun will shrink down to become a tiny white dwarf star, no larger than the Earth. Finally, after thousands of millions of years, the Sun will fade into oblivion. But at least nothing of this sort is likely to happen for a very long time to come. Each time that you go into the garden on a bright sunny day, you will now know what makes the sun shine. You may even like to try safely projecting the sun's image onto a piece of white card to view the sunspots. There is much to see. That is all we have time for this month. Please visit our website, Vimeo, where you can watch all of the past shows of astronomy and space. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back early next year, good evening.